Hello everyone, it's Two More Teachers again. This is the fourth time I'm recording this. First time, I forgot to turn on the recording software. Second time, the recording software refused to behave. The third time, I ended up working on a problem so hard I ended up just fucking it up. And hopefully this will be the last time I'm doing it. So, standard enthalpy changes of formation. Let's go. Standard enthalpy change of formation. Delta HF is the enthalpy change associated with the formation understanding conditions of one mole of substance from its elements in their standard state. What does that actually mean for someone like you? That would translate to um, the enthalpy change associated with going from the elements that make up a compound to the compound under room temperature conditions. What does that imply? Elements in their standard states can have standard enthalpy changes of formation. If you just go from O2 to O2, that's a zero enthalpy change. However, if you go from a different allotrope to the standard state allotrope, that does have an enthalpy change. And then note that the reaction must be written for a mole of product. So if you have something like this, and you want them to have nice even numbers, you're going to have to double it. Enthalpy changes for reaction can be estimated using this mathematical relationship, which is delta HF. L delta H is equal to sum of the delta HF's formation enthalpies of the products times the number of moles of products, subtract the sum of the formation enthalpies of the reactants times the number of moles of reactants. It's just basically has this law. Basically, formation enthalpy is about the closest thing you'll get to enthalpy, like an enthalpy number. You can use it more or less as you would like an enthalpy number, and therefore delta H is just product minus reactant, or final state minus initial state. I know I said in the first episode you can't measure enthalpy, but this is about as good enough as you'll get. And if you use the numbers like that, you won't hurt yourself doing so. Now, let's do a sample problem to really drive the point home. So let's do something like 3C here. Pause the video if you want to try. Now, you'll be given a table of thermodynamic data. So pause the video now, and I'll be going over the solution in 3, 2, 1. Okay, guys, welcome back. So 3C, what's the reaction? NH3 plus HCl yields us NH4Cl. And we know that delta H is equal to this. So it's the formula we discussed like 2 minutes ago, or less than 2 minutes ago. Delta HFR, which when we sub in the values we get 1. I'm just going to leave them blank and fill them in later. So 1 subtract 1. And then looking at our table of thermodynamic data, we get that this is just NH4. Okay, for ammonia, it's minus 80. That should be a 0 there. A 0 there. And for NH... Oh. Oops. I accidentally did this wrong. Hang on. I accidentally wrote this wrong, I just realized, so let's rewrite it. Really having a bad day today if I'm having to record this 4 times, but that's besides the point. So 1, whatever that is, subtract HCl, so 1 of that plus 1 of that. So products minus reactants. So for NH3 it was minus 80, we said. And for HCl, it was for NH4Cl, it's -314. And then for HCl, hydrochloric acid. It is, well, let's find it here. Man, why can't they? Sorry guys, I'm just looking for the stupid thing. Uh, just give me a moment here. We'll find it eventually. Okay, fluorine, bromine. Where's chlorine? B, carbon, carbon, carbon continued. Chlorine HCl is minus 92. And when we plug that into our calculator, we get minus 142. Is it worth going over another one? Probably not. I'll do that in a video worksheet. So until then, to next time.